Hi class, I hope you're all doing well. Welcome to the last week of class. So we've been talking the entire quarter about how to look for life elsewhere in the universe. And today we're finally going to talk about looking for life like us. That is to say, life that's intelligent, life that may be seeking to make contact with other life, and what the challenges may be for us to make contact and understand each other. Okay, so we'll do this in two parts. So the first part, we're going to talk about how to do it. So behind me here, this is a picture of the Very Large Array, which is a telescope in New Mexico, here in the United States. It is 27 different radio dishes. Each of them is identical and quite large. They're on railroad tracks, as you can see down here. Okay, and they can be moved around and they act together as one gigantic telescope. And so sometimes the telescope can be made very small, sometimes it can be made very large, and there's different kinds of science you can do with that depending on what your goals are. So those of you who have seen the movie Contact, this is the array there where Jodie Foster is listening on her headphones to the signals from space. You can visit the VLA when you're not in the pandemic. You can drive to it. It's near Socorro, New Mexico. So if you drive to the west of Socorro, out the highway, it'll take you right across one of the arms of the VLA. There's a visitor center there where you can go visit. And it is really quite spectacular to stand underneath one of these telescopes if you get the chance. So I highly recommend that. Okay, so let me go ahead and start a few slides. So this first part that we're going to talk about today, we're going to talk about, oops, and my slides aren't running. Hang on a sec. This first part that we're going to talk about today is we're going to talk about what we call SETI, the Search for Extraterrestrial Intelligence, and SETI, the Communication with Extraterrestrial Intelligence, and METI, which is Messaging Extraterrestrial Intelligence. So those are the kind of three things that you'll hear people talk about in this endeavor. METI is something new, as we'll discuss, but this is really about us as humans thinking about how we're going to either identify or talk with extraterrestrial intelligences. So we'll define what each one of those things means. We'll talk about how we're actually doing searches. And then right at the end, we'll talk on this question, which everyone always asks, which is, have we actually detected something? Okay, and the answer to that question, just for those of you who aren't going to make it all the way to the end, is no, nothing definitively, but we'll talk about it. Okay? Okay, so what is this all about? So I call this ETI, anything for extraterrestrial intelligence, because we keep changing what that letter A is. So the traditional letter is S, which is the search for extraterrestrial intelligence. And this is really about looking for signals from space that are indicative that they came from intelligent origin, that they weren't just created by something natural, a star exploding, something falling into a black hole, quasar doing something weird, who knows? There's all kinds of things that go on in the universe. There's all kinds of radio signals that we get from the universe that we are confused about what their origin is. And they're signals that could easily be misconstrued as being of intelligent origin. And we've encountered many examples of that as we've been discussing this over the last few weeks. Probably the most notable of these are gamma ray bursts, these gigantic bursts of light that look like there's something trying to get our attention. Those we think are exploding stars or merging neutron stars. And of course, pulsars, which are rotating neutron stars, which look like lighthouses. Okay, so the search for extraterrestrial intelligence is probably, of all of these endeavors, the one we've been engaged in the longest, but it is very difficult because the universe is trying to constantly fool you. METI is actually a new term. So if you are reading the literature on this and you go back 10, 20, 30 years, you almost never hear the acronym METI, but it is new in the sense that you are hearing it more in context with the other acronyms that we're talking about here. And it is very specifically about messaging extraterrestrial intelligences. How is it that we can create signals, we can create messages that we send out to the stars and we intend for receipt by some intelligence other than our own? How do you go about sending them? How do you go about getting them noticed? How do you go about encoding meaningful information in them? Okay, so making understandable messages is really difficult, and we'll talk about that in the second half of lecture today. SETI is something that has been around for a long time. This is communication with extraterrestrial intelligence. And when I say METI is new, what I mean is it's been broken off from SETI. So if you go back and you read old books from the 70s or 80s about this, they will often talk about SETI SETI and SETI CETI. And when they talk about SETI CETI, they mean both one-directional and two-dimensional communications, even though two-directional communications is very impractical. So today, certainly in my mind, and I think if you read the literature, you're beginning to see all three of these terms used. And SETI with a C very specifically means communication with extraterrestrial intelligence. That's always been the acronym, but what it means is messages exchanged back and forth. Okay, now that's extraordinarily impractical, but by and large, it's the sort of thing we all imagine when we talk about trying to find intelligent life in the universe and quote unquote having a conversation. Okay? Okay, so let's talk about SETI, SETI, the most, because it's by far and away the most dominant of all of these. Okay? So there's all kinds of ways we can look for signals from outer space. So one way is to look for unintegrated signals, signals that an alien civilization may have sent out, not necessarily with the intent of communicating with us, but if we were able to detect them, then it would indicate to us that they were of intelligent origin. And one of the easiest ways to think about that is to use Earth as an example. The Earth is constantly leaking radio signals out to outer space. Those radio signals are signals that we produce for ourselves, intended for ourselves, but we aren't careful about how we send them back and forth. And this has been the history of radio communication on Earth since it began in the late 1800s and through the 1900s. Okay, so this is a very common kind of map you see. So Earth is down at the bottom of this image. As you go outward towards the top of the image, you'll see stars at various distances. I've labeled the distances in light years there approximately on the left-hand side. And then you see these arcs. And those arcs are supposed to represent the radio signals from Earth that have been leaking off of Earth because we broadcast TV signals and we broadcast radio stations and we make CD transmissions and all those things that we do that produce radio signals, they leak out into space. And so the question is, how far could they have gotten into outer space by today? So what star could be receiving those signals that we transmitted a long time ago? So if you start down there near the bottom, so something we've talked about many times in this course is Cosmos by Carl Sagan. That was first broadcast in 1980. And you can see there it's about 40 light years away now. So this is about a 5-year-old map, but it's somewhere near the star Pollux, okay? If you go back to the moon landings, which happened in 1969, the TV transmission of the moon landings has been moving outward much longer than Carl Sagan's Cosmos, and it's currently almost to the star Capella, okay? If you go all the way back to the very first fireside chat made by President Roosevelt in 1933, so this was between the world wars after the first Great Depression, that has just passed the star Regulus. Okay, and the first commercial radio broadcast made in 1920 is now past the star Gamma Crucius. Okay, so these radio signals are propagating outward into space. They're getting weaker all the time because as they go farther and farther away, the 1/r² law makes them weaker, but nonetheless, they are traveling out into space. And if you had a large enough telescope, maybe even larger than the VLA telescopes here behind me, you may be able to detect those whispers of Earth that are transmitting themselves slowly outward into the cosmos. Now, what you're supposed to get from this message, or from this image, is that the stars are really far away. And so even at the speed of light, it takes messages a long, long time to get out there. And so if you were to imagine that an alien civilization on any one of these stars received our radio broadcast, they might decode it, they might respond to it, send a message back to us. The round trip signal time is enormous. And so by the time that Regulans have detected the signal from President Roosevelt's fireside chat in 1933, we are nearly a century beyond that. And we are a different civilization in many ways, with different technology, different capabilities, different history even, than that first fireside chat. And by the time the Regulans might decode it and send a message back to us, will be another 90 years in the future. And so we will be even more different then. Okay? So one of the kind of fun exercises to do is to imagine, what if your parents sent a radio signal out to outer space, they broadcast your baby picture to aliens on some distant world to announce your presence, right? So how far away could that be? So assuming most of you are kind of almost 20 or so, and you were born in 1999, 2000, 2001, 2002, 2003, I just went and looked at the closest stars in the closest stars list, and these are the rough starred stars where your parents' announcement of your birth could have slowly made itself to the stars. Okay, so I'm beginning to think this might be a really good business to have, right? Parents could ask me to broadcast their baby pictures to the stars so aliens knew you were here. So maybe I'll make a fortune like that after the pandemic. Okay, now this is assuming that a civilization broadcasts radio signals. And we do assume that that is likely to be the natural trajectory in the development of technology. Very uncontrolled generation of radio signals is easy. The earliest technology, the same technology used to broadcast radio signals, is very closely related to the technology to receive radio signals. So we assume this is a standard technology. But there's an interesting thing to think about, which is that a civilization over time can and may become radio quiet. So what do we mean by that? So when we first started broadcasting radio and television, it was like this. We have a transmitter at one place in the world. We constantly send out the signals, okay? And those signals eventually arrive at their destination, which are individual people's homes, radio signals, their cars, whatever. But the signals don't know to just go to those houses. They also get broadcast out into space. That's what we mean when we say the signals get leaked into space, okay? And so we did this like for almost a century. Okay, but for those of you who have seen old television, or if you ask your parents about what life was like when they watched old television, in the olden days, signals broadcast in this way through antennas were not always great. Okay, and this is a screen capture of what the original broadcast of the lunar landing looked like. And you can see not only is the signal from the moon broadcast on radio kind of grainy and kind of fuzzy, but the TV reception itself was kind of fuzzy. And so the development of communications technology has always been towards how do you improve on this? Okay, and one way you can improve on that is you can make your radio signals really loud, okay, or you can change the technology that you're using. And so we've gone from this, the way things were done in my parents' and your parents' or your grandparents' day, to what we have today, which is we send everything over cable. And then when it gets to its destination, we broadcast it over very low power Wi-Fi. So it comes into your house over a cable into a cable router, and then you have a Wi-Fi hotpoint that broadcasts your TV show or your music on Spotify or whatever to your phone. Okay, and those are low power radio signals, so they don't leak off of the earth because they don't have enough energy to get off of the earth. And so if you're an alien out there in outer space, what's eventually going to happen is our civilization is going to become radio quiet. The outgoing leaking signals, we used to broadcast President Roosevelt and I Love Lucy and the NFL Super Bowl and all of that stuff's going out into outer space, but eventually it's going to simply taper off and vanish because we're broadcasting everything over wires and low power Wi-Fi now, okay? Our civilization will look like it's vanished if aliens are sitting out there watching our radio transmissions, okay? So that's a very interesting notion, because the reason it's really interesting is because that is one resolution to the Fermi paradox. The reason we haven't detected any alien civilizations yet is because eventually radio civilizations go radio quiet. They learn to control their emissions either by design or because it's better technology. And so there's only a very small brief period of time where we might be able to detect radio signals from them. Okay? So that's one resolution. Now, this is for accidental transmissions, right? I'm just kind of broadcasting signals that go out to space. But the other mode of searching for extraterrestrial intelligence is to search for very deliberate signals, signals that were sent by a civilization with the express intent of communicating with another one or attracting the attention of another one. Okay, so what's that all like? Well, we've talked about this a little bit before, and the main problem, as we've said, is how do you get someone's attention? How do you say, hey, we're here, pay attention to us, we have a message we're about to send you, okay? Well, there's many issues surrounding that you have to imagine have to be overcome. The first is you can't send messages to every star you see in the sky. You could, it would take a long time, okay? So you want to send it to someone. If you're trying to get someone's attention so that you can either tell them about yourselves or so that you can carry on the conversation with them, you want to make sure that you pick a star where someone's there already, and they might receive and return your signal. Okay, it takes so long for the messages to get out there that you don't want to just kind of randomly send things out there, although that's what we're doing, as we'll discuss. Okay, part of the resolution to this problem is the exoplanet searches that we've talked about already. If you can identify a likely candidate where there is a world that has biosignatures, or a world that's in the habitable zone that has, properties similar to the Earth, you may think that's a good target. So that helps you select from the 400 billion stars in the galaxy the right ones to send to. Okay? The other issue that you have to face when you're trying to get someone's attention is, how do you make the signal noticeable? Well, one way to make the signal noticeable is to make it extraordinarily bright. Make it so much brighter or louder than any other signal you might see in nature. So one of the questions is, how might you do that? Well, you probably had some experience with this, okay? So imagine you have a flashlight. So if you just have a flashlight and you turn it on, okay, it makes some beam of light, which up close is very bright, but as you get farther and farther away from the signal, it gets dimmer. Okay, so that's not really useful if you want to attract someone's attention with your flashlight. But some of you may have a focusing flashlight. So if you twist the focus of the flashlight, you can take that super wide beam and you can make it much narrower so it concentrates more of the energy so it looks brighter at much greater distances. Okay, so this is a strategy if you're trying to get someone's attention, is you can send a very bright focused beam of energy in the form of radio light or laser light or whatever you want in a given direction in order to make your signal more noticeable. Now, this is an idea that's been around for a long, long time, but we've only recently started thinking seriously about how to search for this. And so if you go out and you read the SETI literature, you'll start to hear about something called laser SETI, searches for very high energy directed laser signals that we think are with the intent of trying to attract our attention. And then kind of more, less energetically, what we call optical SETI, looking for optical signatures of a distant civilization. And we talked a little bit about that earlier when we were talking about how far away could you detect an atomic explosion from. Okay, that would be an example of optical SETI. But there's also deliberate optical SETI, deliberately sending out optical signals that might be detectable. Okay, so those are interesting branches of SETI that are, I think, slowly becoming more prominent and people are starting to think seriously about. Now, one of the last problems you have when you're picking one of those stars up there at the top to send a signal to is, if you aim at the star, you got to make sure you hit the star. Okay, and that kind of precision technology is really hard. Okay, and the way what we mean by it's really hard is to imagine we were here on Earth trying to send a signal to a solar system about the same size as ours, but 10 light years away. Okay, how accurately would we have to point our telescope or our laser or whatever it is in order to hit that solar system that's 10 light years away? Well, that's a matter of an angle. How far do I have to tip my laser or my telescope back and forth before I shoot my signal? And the accuracy of that aiming has to be 0.009 degrees, 9/1000ths of a degree. Okay, that's pretty accurate. Okay, and that takes a little bit of doing. It takes a little bit of accuracy, and it takes a little bit of technology to make that sort of thing happen. Okay, so there's a whole host of challenges in order for people to send signals. But we're thinking about how to do this. We're trying to imagine how might we send signals. We'll talk about that in the second half of the lecture today. So we can imagine that if there are advanced extraterrestrial civilizations, they might also be attempting to overcome these signals. And so part of our SETI searches are founded on the principle that some alien civilization has figured out these problems, has decided Earth is a good target, and sent a signal our way. Okay? So how do we search for those signals? Okay, well, let me show you an example. So we're basically searching for radio signals. Okay, now you and I receive radio signals all the time, or in the olden days we did before we had Spotify and stuff like that. But you would receive a radio signal, and your radio would take that radio data and decode it and turn it into something you can understand. Okay, so you and I, being auditory beings, we turn those radio signals into sound. We can also turn them into pictures. Okay, so this is an example of how you turn radio signals into pictures. Rather than turning them into sound, you can turn them into pictures. And what we do, that picture that scientists like is something called a spectrogram. Okay, now a spectrogram is a way of looking at all the different pieces of the radio light, that is to say, all the different wavelengths of radio light that we get, and asking how much of each radio wavelength do we have that makes up this signal. Now, one of the things that you learn if you take physics is that there are two ways of representing the color of light, or of representing the radio waves that you're talking about. Wavelength is one of them, but frequency is another. Okay, and as I note here in the note, frequency is simply related to wavelength by the speed of light. You can just convert the two numbers into each other. So frequency is often a much easier way for us to think about radio signals because we're used to thinking about frequencies in the context of other waves, in particular in the context of sound waves. We have lots of intuition about how to think about frequencies of sound waves. Okay, now you may think, whoa, that sounds strange. I've never thought about that. But most of us have seen this in the form of a spectrum analyzer on our stereo. Okay, so what's a spectrum analyzer on a stereo do? So this still frame here, and this is a movie, I'll play it for you in a minute. What it does is it looks at all the sound waves coming in, and it says, okay, there are low frequency sound waves, what you and I might call bass. There are mid-tone sound waves, and there are high frequency sound waves, what we might call treble. And so what the spectrum analyzer does is it takes any sound and it basically tells you how much bass do I have, how much mid-tone do I have, and how much treble do I have. And as the sound fluctuates up and down, the spectrum analyzer says you have more bass now or you have more treble now. We can do the exact same thing with radio signals because there are low frequency or long wavelength radio signals, there are middle frequency or medium wavelength radio signals, and high frequency or short wavelength signals. And a spectrum analyzer would go up and down in exactly the same way that a sound spectrum analyzer would. Okay, so this is a movie. This is just a spectrum analyzer I have on my phone. The phone just listens to what's going on. It listens to your voice, it listens to your music or whatever, and it shows you what the different spectrum analysis of that sound looks like. So I just made a movie of my phone so you can see what it looks like, and then I'll show you what a SETI spectrum analyzer looks like. Okay, so let me play this movie.
Hi class, this is an example of a frequency analyzer. It's the same sort of thing that we use to look at any kind of signal that has frequencies and waves in it. You'll see here as I talk, different levels go up and down. It's dynamically controlling what it shows you, so when things change, it jumps way up. On the left are low frequencies, and on the right are higher frequencies. So left is long wavelength, and right is higher wavelength. If I whistle, you'll see that. And if I play music, you'll see music is equally complex. Okay, so that's an example, and we can do the exact same kind of analysis and same kind of display by analyzing radio signals like we just analyzed sound signals here.
Okay, so that's an example of what spectrum analysis looks like. So you can take any wave you get, a radio signal wave, sound waves, any waves you encounter, and decompose them into a spectrum this way. So SETI analysis is the same way. So this is an example of what a frequency spectrogram, as we call them, looks like for a SETI analysis program. So this is from a citizen science project called SETI at Home. We have been collecting radio data for a long, long time, and the searches for radio signals are very computer intensive. And so what we did is we just send all of this data over to individual people's computers. And when your computer's not doing anything, it's just running a screensaver or something like that, then it analyzes the radio signals looking for signals from extraterrestrial intelligence in the background. So this is a program that's been going on and running now for, boy, almost 20 years or so. And as it turns out, just a month ago, they put it into hibernation because they've analyzed all their data multiple times. They're going to write a scientific paper. As more data gets collected, it will be likely turned back on eventually for people to help with the analysis. But this is what the display looks like. So you can see there the frequency moves across from the left side to the right side. Power is, that is how strongly does a given frequency contribute, goes up. So you can see lots of different spikes. And then what you see going back into the screen are the frequencies taken at different periods of time. Okay, so this is an example of what the SETI data looks like, and we look for signals in the SETI data by looking for very specific frequencies which look abnormal and looking for patterns among the frequencies which look abnormal. We'll talk a little bit more about that in the next half of lecture today. So there have been many, many SETI searches over the years, but right now there is a dedicated search going on. It is being led by the SETI Institute in California. They're a nonprofit organization dedicated to the search for extraterrestrial intelligence. They've had a lot of philanthropic support, in particular from Paul Allen, who used to be at Microsoft. He dedicated a large sum of money to build the initial configuration of what's now called the Allen Telescope Array. So this is a dedicated 42-dish array in Northern California. You can see a picture of them here on the field. They do science with this, but they dedicate time all the time to looking for signals of extraterrestrial intelligence with it as well. The goal is to expand that array to 350 dishes. They'll do that in a couple of stages. What they do is they built this up to this 42-dish array. They're doing some tests and analysis, trying to understand how to make the array better, how to make their telescopes work together, how to make them more sensitive. Once that analysis is in, they'll jump up to, I think, about 100, then about to 200, and then finally to the full 300 dishes. Okay, so this is the current dedicated array. Most of the searches before this array have been done by getting time on professional radio telescopes, where they've been using the searches for other science. And so the folks trying to do SETI would write proposals to do their SETI searches in exactly the same way that you and I might write a proposal to search for black hole emissions or to search for radio galaxies or map hydrogen emission in the galaxy. You would write a proposal to search for extraterrestrial signals. Okay? So this is kind of where we're at. Okay, so SETI is kind of, we have strategies for doing it, and the question is, we've been doing it for a long time, and what everyone wants to know is, have we ever detected anything? Well, there's lots of things we've detected. There's lots of natural things we've detected. There's a few things that we don't really understand, but we think they're probably of natural origin. But there have been a few events that we really don't have good explanations for. So let me tell you about the most famous one, okay? So the most famous one was detected here at the Big Ear Radio Telescope in Ohio. So this was operated from 1963 to 1998 on the observatory grounds of Ohio Wesleyan University. Okay, so this doesn't quite look like the kind of radio telescope that you're used to, like the VLA here behind me, okay? But it is a radio telescope. It's kind of a funny one. So the radio signals come in from the sky. They hit this big flat screen here, okay? And it reflects them to this curved screen. And this curved screen is like a curved mirror. It reflects everything back to a point, it focuses it, and the radio detector is right there. So this telescope's basically looking straight up, and as the Earth rotates, it pans across the sky, okay? So on the 15th of August in 1977, they detected a very bright, very loud, very unexpected signal that is called the wow signal. And the reason it's called the wow signal is because the scientist who was reviewing the data a couple of days after the signal was detected saw it and circled it and wrote wow next to it. So this is a picture of the actual data stream. Now you'll notice this is in the olden days. This is 1977, right? So in those days, everything was still spun out on paper, and you had to take all the data off the paper and convert it into graphs. That's something that happens automatically on our computers now. Very seldom do we look at raw data like this. It turns it into graphs automatically. But we can take this signal, so that, that 6EQUJ5, those are all indicators about how strong the radio signal was in the data, but you can turn it into a graph. And if you turn it into a graph, this is what the signal looks like, okay? So it lasted about 72 seconds long. And so the signal was going along. It was what we would normally call static, so these little horizontal bars, that's about the height, the strength of the normal static. And it's static like static. It's if you were to listen to it on a set of headphones. But then all of a sudden, the signal jumped way up, and it stayed way up, and then it came way down, and then it stayed way down, okay? And what's remarkable about this signal is its height and its symmetry and how much stronger it is than the static. So when this signal was going on, it would sound like a normal signal to you, but the static would just be that little kind of faint static you hear when the signal's really strong and you're listening to the radio, okay? So it came from the general direction of the galactic center, but we've never seen it repeated, okay? And we have tried many times to explain it by many types of astrophysical phenomena, but there has never been an astrophysical phenomena that we have detected either somewhere else in the universe or been able to simulate or be able to explain based on other observations that gives a signal profile that looks like this. Okay, so that's called the wow signal, and it is one of the most stunning examples of an unknown signal that we don't understand. It's the sort of thing you could imagine that might be sent out to gain attention, but there's nothing about it that has any information. There's nothing about it that has any kind of encoding that represents any other kind of data or anything. It's just this bright burst of radio light that has this very nice symmetric quality and came from a direction in the galaxy that we thought was nominally quite interesting. But we have no idea what it is. Okay, we've never seen anything else like it either. So, who knows? And so we keep looking. We keep studying this signal. Every couple of years, someone comes back with some explanation for maybe it's this. And in each of those instances, we've never been able to convince ourselves definitively that it is of natural origin and not just trying to get our attention. Okay, so that's quite interesting. And, we'll see what the future holds. Okay, so that's all I'm going to say about SETI. We're going to talk in the second half of lecture about the Arecibo message. So I'll talk to you all in a little bit. Take care of yourselves, and I'll talk to you soon.